Hello guys, today we are presenting our project titled Lightweight Output Refinement for Improving YOLO-Based Shelling Status Detection. This project is a collaboration between Charlotte Dai, Xin Chanzhu, and Yue Qiwen. So our contents include 5 parts, and I will start from the introduction. First, I would like to emphasize the critical role of agricultural products quality control. Nuts, fruits, and grains are essential to global food supply chains, influencing both food security and market competitiveness. Consistent quality is crucial for food safety, consumer trust, and maintaining a competitive edge. Defect inspection plays a key role by identifying and removing defective products before they reach the market. Although modern processing plants integrate mechanical system for shelling, sorting, and grading, challenges in quality inspection still persist. Traditionally, manual vision inspection has been the most widely used method for food quality control. While effective to some extent, this method suffers from several major limitations. First, it's time consuming and labor intensive. Second, it's prone to human errors due to fatigue or inconstant standards between inspectors. Furthermore, maintaining high precision and consistency across large production batches is extremely challenging. Finally, manual inspection is not scalable for handling the growing demands of global food markets. In response to these issues, early computer vision methods emerged. So early computer vision enables basic object recognition, but deep learning, especially CNNs, greatly improve defect detection by achieving higher accuracy and faster processing. Yet, challenges remain, as deep models demand high computational resources, are hard to interpret, and struggle to detect subtle or hidden defects due to limited long-range feature capture. For example, in pecan defect detection, fine cracks may only appear on one side of the nut, and when the pecan is flipped during inspection, the side without visible cracks might be exposed, leading to a misclassification as a normal pecan. Such cases highlight the limitations of current model in handling complex real-world defect scenarios. Given these limitations, the motivation for further research is clear. Industries now demand higher detection accuracy under strict resource constraints, such as limited GPU capacity and faster inference needs. They also require real-time, consistent quality control and more intuitive, human-friendly interactions methods like natural languages-based reporting. However, no current system fully balances accuracy, efficiency, and usability. Achieving all three remains an urgent challenge, driving the need for innovative solutions in defect detection. Now we are going to see this part of experimental setup.
Thank you, Qingchan. As she currently mentioned, we encounter an issue where some cracked pecan are difficult to detect, especially after flipping, which may cause detection result to mismatch pseudo ground truth. To address this problem, we propose an adaptive refinement framework. First, we train a YOLO-V12-based detection model to perform initial detection on video frame. Then, we introduce a lightweight refinement model to further correct the detection result and enhance reliability. Finally, fine-tune LLMs is included to adaptively adjust the model parameters, such as detection threshold, based on the refinement output and user instructions. Due to the time constraints, we have so far completed the detection model and refinement model components, and in this stage, we only utilize 2 classes, which is cracked and uncracked, from the YOLO model instead of 4-6 classes setup. This is the detection model. We train a YOLO-V12-based model on our own pecan dataset. The model classifies pecan cracking condition into 6 categories. Here, you can see a sample detection result. In order to train the refinement models, we first need to extract features. From each frame in the window of videos, we collect 2 types of information. First, the detection metadata. Here's which includes like track ID, frame IDs, bounding box detection scores, and protection labels, ground truth labels, and so on and so forth. Second is vision features. We applied ROIs to extract the feature map corresponding to the detection bounding box. Especially the vision features extract from two different layers. The first one is 14th layers, which is A2C2F blocks, and the second one is 20th layers, which is C3K2 blocks of the YOLO-V12 models. These two capturing the mid-level and high-level representation respectively. Here is a sample of the extract features and the metadata. On the left, we show the visualized feature map from the two different network layers, and on the right, we represent the associated detection metadata along with the flattened feature vectors. We explore several strategies, includes sliding windows and two machine learning methods, support vector machine and random forest, two sequence models, RNN and transformers models, and lightweight large language model, which is Llama 3.1 8B. Due to time limitation, I will not go into too much detail about the algorithms. The idea behind the sliding window is simple. We maintain a fixed size window and define two thresholds. By compare the proportion of cracked and uncracked label within the window against their threshold, we determine the final predicted label. For the SVM, we use track ID, bounding box, score, predict label, and two feature map vectors as input features. Then we apply a slide window over the track and do aggregation by min or max pulleys. And then we train the SVM using RBF kernel. We use the same strategies for random forest model. For the RN model, we adopt a hierarchical temporal aggregation strategy to prepare the input sequence. Similarly, we first define a frame level sliding windows to do aggregation. And then we define a second slide window, which is a sequence length to construct the input sequence. Same with the encoder-only transformer. For the LLMs, we aggregate features and construct the instruction style prompts following the Allega template, and fine-tune the Llama 3.1 models using LoRa adaptation. Here is our experiment setup. All the experiments were conducted on the NVIDIA A100 GPU using PyTorch 2.6.0 and CUDA 12.4. For YOLO training, we use our own pickup datasets consisting of 3,985 images for training set and 500 images each for the validation and test set respectively.
This slide shows the data preprocessing pipeline for the random forest model. The input is JSON-like file, which is generated by running YOLO on the packet crabbing video. From the original multi-class labels, we only retain label 1, which is crabbed, and label 5, which is uncrabbed. Next, we divide the filter data into training, validation, and test set using an 80-10-10 split. In this step, we train the random forest classifier on the preprocessed dataset. Before model training, we apply the min pooling over the sliding window to aggregate the frame-level features into the window-level representations. The model is trained using the default number of 100 estimators, which typically provides the stable and strong classification performance without the significantly increasing training time. And finally, we evaluate the model on the test set by calculating both accuracy and the confusion metrics. This slide outlines the setup for the support vector machine model. The data preprocessing pipeline is identical to that of the random forest model. For the classification model, we use the SVC with an RBF kernel, which enables nonlinear decision boundaries by mapping the input features into a high-dimensional space. We set the regularization parameter C to 1.0, which balances the trade-off between the minimizing the training error and maximizing the margin. The gamma scale equal scale setting automatically adjusts the kernel's flexibility based on the data, essentially controlling the reach of the RBF kernel in the transformed feature space. We also applied feature normalization through a standard scaler, ensuring the SVM operates on the features with a consistent scale. This figure shows how the accuracy and F1 score of SVM and random forest evolves as the sliding window size increases. In the subplot A, we observe that SVM performance improves steadily with a larger window size, and reaching its peak accuracy and F1 score around a window size of 40. In contrast, the subplot B shows the results for the random forest, which exhibits a more fluctuating F1 score curve, especially at larger window sizes. Nevertheless, its best performance appears near a window size of 140, indicating that the random forest model may require more aggregated temporal context to perform optimally. Overall, the SVM model is more stable and achieves optimal performance with a smaller window, while the random forest is more sensitive to the window size, but can achieve comparable results when tuned appropriately. We can observe that all refinement methods outperform the baseline YOLO-V12 model. The sliding window method offers a good trade-off, achieving a macro F1 score of 0.7320 with a fastest inference time of just 0.001 millisecond, make it ideal for the real-time industrial deployment. Among the traditional machine learning methods, FVM refinement achieves the best performance with the highest accuracy of 0.9870 and the highest macro F1 of 0.9580, while also have a relatively low inference time of 0.084 millisecond, which is significantly faster than the random forest. And random forest also perform well, but it is slightly slower with an inference time of 0.185 millisecond. For sequential models, both RNN and transformer achieve strong performance with macro F1 scores above the 0.90 and inference times under the 0.1 millisecond. Notably, transformer achieves perfect accuracy under a small window setting of frame window size 3 and sequence length 5, making it the most efficient and accurate method in the sequence category. And finally, while the fine-tuned large language model shows more improvement over the baseline, it suffers from the severe prediction collapse and extremely high latency, which renders it impractically in the latency-sensitive application. In conclusion, among all methods, transformer-based refinement achieved the best overall performance, reaching the perfect accuracy under the minimal window setting, which demonstrated strong efficiency and robustness. SVM delivers the highest macro F1 score while maintaining the low inference time, making it the most balanced choice among the traditional machine learning methods. The sliding window method, though slightly lower in performance, offers the fastest inference by far, making it ideal for the real-time scenarios. In contrast, the fine-tuned large language model suffers from the prediction collapse and the extremely high latency, highlighting its limitations for the lightweight and the time-sensitive refinement task. And in the future work, we will explore the fine-tuning large language models such as the Cuban or Lava to enhance adaptive output refinement and the dynamic decision-making. We will also expand the current dataset, which is small and highly imbalanced, and extend the preliminary 2-class classification to a full 6-class defect categorization. At last, we will investigate to integrate the multimodal data source like video stream, machine parameters, user instructions to enhance the refinement model's understanding and decision accuracy. Thanks for watching.